Our work considers the problem of estimating the relative orientation between a pair of images. This task typically requires estimating corresponding points, such as between the white trunk or the red building in this example. In this work, we want to estimate relative rotations for image pairs that have no overlap. In fact, they could be facing in entirely different directions. For such pairs, there are no correspondences, and so traditional methods fail. How can we solve this problem? First, let's consider what people can tell by looking at such extreme non-overlapping images. In fact, there is a wealth of information we can use. For example, can use illumination cues. For the left image pair, we can reason about the light direction and the resulting shading of the building facades. We can also use geometric priors. For example, we can find sets of parallel lines in the scene and understand how these lines and their vanishing points relate to one another. These kinds of cues do not take the form of direct correspondences, but instead are implicit or hidden cues that provide evidence for the relative orientation. But how can we teach a machine to use these cues? We could take a fully supervised approach and, for instance, label vanishing points, light directions, and perhaps some additional cues, then learn to predict these elements from the images. This could work, but requires additional supervision, and more generally, we don't want to restrict our model to a set of handcrafted cues, which may or may not be relevant for the image pair provided at test time. So, in our work, we guide the network to learn and reason about hidden cues implicitly. Our approach is inspired by traditional methods that accumulate evidence for global quantities like vanishing points or image orientations from local evidence via voting streams like Hopf transforms. In particular, we accumulate local evidence from all pairs of local patches. For example, this purple pair could give evidence, for example, for how vanishing point locations are related in the two images, and this yellow pair could give evidence for light source directions. The key insight here is that if we want to reason about global quantities, such as vanishing points, any two patches could provide evidence for the global geometric relationship, no matter their spatial relationship. Our method first extracts dense feature descriptors from each image. We perform all pairs local correlations to obtain a 4D correlation volume, and then feed this correlation volume to a neural network that predicts the relative rotation in the form of a distribution over rotation angles. The idea is that this 4D correlation volume is rich with information and encodes a variety of hidden cues that allow the network to infer a relative rotation even for challenging non-overlapping pairs. This entire system, including feature extraction and orientation prediction, can be trained end-to-end on image pairs with known relative poles. We evaluate our method on a large variety of extreme RGB image pairs, including indoor and outdoor images captured in different geographic locations under varying illumination. Our evaluation shows that our model can successfully estimate relative rotations among non-overlapping images, showing significant improvements over baseline regression models, including the methods by N et al. And Jordan et al. Presented here, for the indoor interior net and Sun 360 datasets, and also for the outdoor StreetLearn dataset. At the same time, our method does not compromise performance over overlapping image pairs. Please check out our project page and paper for more details. Thank you.